Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. In this lesson, we'll be looking at the engineering economics for retrofitting operations, and we'll be using incremental analysis to do so. So typically, the first question students have is, what really do we mean by retrofitting? Now, this assumes that we've got a working process that's making a profit, and we're considering adding a piece of equipment to the process that would, make the process more profitable. So some examples might be that maybe you want to add insulation to a heat exchanger, or maybe you want to add some sort of online sensor to a control system instead of a more difficult, challenging, you have to take a sample and run it to a lab. Maybe you want to change the trays in a tower to packing. All of these are the kinds of things that are considered retrofitting. Part of what makes it retrofitting is that you don't have to do it. There's always the do-nothing alternative. The process is working already, so these are optional. To do retrofitting analysis, usually we are talking about small purchases. So therefore we can do these using non-discounted, quicker techniques. Sure, discounting is always a better way, but non-discounting can be used very successfully in these small budget purchases. Now we want to use incremental analysis because we want to determine whether or not this additional spending is actually worth it. So we can do this using either rate of return analysis on our incremental investment or a payback period analysis would be two common ways of analyzing this. And because we haven't used these in a while, remember that the rate of return on investment with a non-discounted would be the annual savings, the positives over the annual or the total investment, which is the cost, the negatives. But here we're looking at the incremental values of these. For payback period, it's going to be the amount of savings divided by our annual, or the amount that we've spent, investment, over our annual savings. And again, we want these to be the incremental values. So let's look at this in practice. We have some insulations that are being considered for the heating loop on an endothermic reactor. So it's really important that we keep the temperature where, we've designed it to be. We're going to use a non-discounted rate of return rate of 15%, okay, which is equivalent to a payback period of 6.7 years. And this is going to be the hurdle rate for any improvements such as this for our company. And we want to determine which alternative is best. Now, one option is we don't add any insulation, so that's alternative one. I have two types of insulation, insulation A, insulation B, and they could be either 1 inch thick or 2 inch thick. The project costs and the annual savings are documented over here. So, how would we like to analyze this? Let's look at both methods, the rate of return on our incremental investment and the incremental payback period. So the rate of return on investment for this incremental change, I'm going to first start by comparing to the lowest cost option. This works just like we did when we did incremental analysis on large projects. So we're always comparing to the lowest capital cost first. And that's option one, which is do nothing. So this is really the rate of return on investment for those individual processes. And what we see here is that option 2 has the best rate of return when compared to doing nothing. And it's good. It's much higher than what we were told we were looking for, 15%. And we also have our incremental payback period is 2.1 years. Remember, in payback period, we want the fewest number of years. So option 2 right now is the one with the lowest cost that meets our profitability criterion. Okay, and we're going to now take this as our base case and compare the others to option 2. So when we look at option 2 and compare option 3, we see that, all right, 1900 minus 1400 is 100, 5000 minus 3000 is 2000, and that gives me 25%. So this 25% is still more than my 15%. The payback period is 4, still less than the 6.7 years. So this means option 3 is my best case. Okay, so I'm going to now compare any higher cost alternatives to option 3. So comparing 4 to 3, we get a 10% return, which is less than the 15%. Comparing 5 to 3, we get a 10.6% return, which is also less than our option 3, less than the 15% that we wanted. The payback periods on these are greater than 6.7 years, and so therefore our best choice is option 3. What if we wanted to do these using discounting? Well, we can do these again. Any of the techniques should be equivalent, but we're going to be doing it on the increment. And we could do this with net present value or the equivalent annual operating cost. Always we're going to consider the do-nothing alternative. And we're going to choose the one that has the highest net present value or the lowest operating cost. So again, comparing to option 2, or option 1, excuse me. Comparing option 2 to option 1, I need to use discounting at the 10% rate, and this incremental net present value in this case is 2,307. Okay, so that's good, and in fact it's higher than any of my other options. And when I look at this, I see that option 5 is negative, so that's not going to be a good choice. So option 2 is my best choice at this point in time. If I switch and look at this using EAOC, I can again see that this would be my best choice. I could go through and compare now the other alternatives to option 2, okay, which is my best choice at this point in time. In this case, it will turn out that option 2 is your best choice. So this concludes our various economic analysis tools. What we will be looking at next is the concept of risk analysis. Thank you very much.